Welcome everyone. This is the first video in estimation theory. In this video, I will talk about basics of estimation theory and I will talk about unbiased estimator, which is one of the characteristic for a estimator to be good estimator. My request to you is that watch the video till the very end so that you do not miss any concept. I am going to solve multiple problems through which you will be able to understand estimation theory in detail. So let's start. In case if you are new to the channel, you should subscribe the channel as well. So first of all, let us understand what is estimation theory. So to understand estimation theory, let us take this example that suppose you want to estimate the average income of your city, right? Suppose the population of your city is 2 million, right? And you want to estimate the average income of your city. So now it is practically very difficult to go to all the 2 million people and ask them one by one that what is your income and then calculates the average income. So that is a very time consuming and tedious job. But what we can do, we can take a random sample. First of all, let us be clear about this term, that is the random sample. By random sample, what we mean that I have drawn the sample without any bias and each element in the population has the equal probability to be part of the sample, right? So from this sample, suppose I take a sample of 2000 people, right? And I ask them that what is your average income, and based on this average income, suppose we estimate the average income of the population. So this process is known as estimation. So to understand it in detail, let us first understand some of the basic terminology that we are going to use. So here we have two things, one is sample and another is population, right? So if I talk about any term associated with population, that is known as parameter, right? And if I talk about any term associated with sample, that is known as statistics. So this is what I have written here, that statistical constant of the population, like mean of the population, variance of the population, or median of the population, or any other term associated with population, that we call as parameters. And a statistical measure which are computed from the sample observation alone, like mean of the sample, variance of the sample, these terms are known as statistics, right? What is a statistical inference? The objective of sampling, means the process of drawing the sample, is called sampling. So the objective of sampling is to study the features of the population on the basis of sample observation. A carefully selected sample is expected to reveal these features, and hence we should be able to infer about the population from a statistical analysis of the sample. This process is known as statistical inference, means that we take a sample, we study the sample, and based on the study of sample we conclude something about population. So basically there are two types of problem. Firstly, we may have no information at all about the characteristic of population. So the first thing is that suppose we have a population, and for population we don't know anything, that what is the characteristic of that population. And suppose we don't know any value of the parameter which is involved in the distribution, and suppose it is required to estimate these parameters. So what basically they are saying, let me summarize it so that you do not miss, that suppose we have a big population and we do not know anything about this population, no information is available, no information, right? And what we are doing, we are taking a sample, and based on this sample we are estimating some of the parameters associated with the population, and in particular we are estimating the parameters which are defining the distribution. For example, suppose we have a normal population, and for the normal population, for defining the distribution, we need two parameters, that is mu and sigma square. So suppose I want to estimate what is the value of mu and what is the value of sigma square. So this process of estimating the value of the parameters that we are associating with population is known as problem of estimation. Another problem here is that suppose some information or hypothetical values of the parameters may be available, and it is required to test how far the hypothesis is reasonable in the light of information provided by the sample. This problem is test of hypothesis. So we are going to talk about testing of hypothesis in the coming videos. In the next few videos, I will be talking about problem of estimation. Okay. So what is the problem of estimation? So to understand it, let us understand this process. So suppose we have a random sample. We have a random sample x1, x2, xn on a variable x, whose distribution in the population involves an unknown parameter theta. So we have a random sample, and the random sample has been drawn from a population, and from the population that it has been drawn, suppose I want to estimate the value of theta, which is unknown. Theta is a parameter, means theta is a a statistical measure associated with the population. So it is required to find an estimate of theta on the basis of sample values. So on the basis of these sample values that I have got, I want to estimate the value of theta. So the estimation can be done in two different ways. One is point estimation and another is interval estimation. So let us quickly understand what is point estimation and interval estimation. In point estimation, the estimated value is given by a single quantity, which is a function of sample observation. The function is called the estimator of the parameter, and the value of the estimator for a particular sample is called estimate. So what I am suggesting, that suppose the same example that I have taken earlier, that you have taken the sample of 2000 families from your city, and based on this sample, suppose you are estimating the value of the average income, that is equal to suppose 4 lakhs per annum, right? So this value is just one value, and since we are estimating just one value, we are calling this as a point estimation. What is interval estimation? So in interval estimation, an interval within which a parameter is expected to lie is given by using two quantities based on sample values. This is known as confidence interval, and the two quantities which are used to specify the interval are known as confidence limit. So like in the same problem, suppose I say that the average income of the population is between 3.4 lakhs to 4 lakhs. So here we are not estimating one particular value, but rather we are estimating an interval. So this is a process of interval estimation. So in this video, in the next few minutes or next 30-40 minutes, I am going to talk about one of the characteristic of point estimation. So what is point estimation? Following are some of the criteria that should be satisfied by a good estimator. And what is the first criteria? The first criteria is unbiasedness. So this type of question usually are asked in MCQ exam, that what are the characteristics of a good estimator. So there are 4 characteristics that I have highlighted here. One is unbiasedness. So the estimator should be unbiased. Another is it should be consistent, it should be efficient, and it should be sufficient. So in the coming videos, we are going to talk about consistency, efficiency, and sufficiency. In this video, I'll be talking about unbiasedness. Okay. So till now I talked about what is estimation all about. So there is a sample, and based on the sample values we estimate something, right? So the process is known as estimation. So what is this unbiasedness? So suppose an estimator is defined with the help of a sample x1, x2, xn. So the estimator is a function of the sample values. So an estimator which I am defining like t of x1, x2, xn is said to be an unbiased estimator of theta if expectation of t is equal to theta. Okay. So this is a very important point. What is the characteristic? That if I calculate the expectation of t, this should be the equal to theta. So theta is the value that I want to estimate. What is t? T is a function which I am defining with the help of a random sample that I have drawn. So this function that I am defining, this is known as estimator, right? And whether it is a good estimator or not, that we decide by calculating the expectation of this. If expectation of this is equal to theta, then it is said to be a good estimator. If expectation of t is greater than theta, then t is said to be positively biased. And if expectation of t is less than theta, then t is said to be negatively biased. The value of bias is given by b theta, which is expectation of t minus theta. So you remember these terms, they may ask you in multiple choice question. Now what I am going to do next is I am going to solve multiple problems, and each of these problems are very important. So you must understand it very carefully. So the first problem is that let x1, x2, xn is a random sample from a normal population whose mean is mu and variance is 1. We have to prove that this t that I am defining with the help of these sample values is an unbiased estimator of mu square plus 1. Mu square plus 1 is something which is associated with the population. So what is the process? The process is that we need to show that expectation of t is equal to mu square plus 1. This is what we have to show. So let us try to do that. So I am calculating the expectation of t. That is equal to expectation of 1 by n into summation xi square. I varies from 1 to n. So basically this is what? This is expectation of 1 by n. For our convenience I am writing it x1 square, x2 square up to xn square. And there is a property of expectation. So using the property of the expectation, it can be written as 1 by n into expectation of x1 square plus expectation of x2 square up to expectation of xn square. Right. This is because of the property of estimation. Now I need to calculate what is expectation of x1 square, x2 square, xn square. And it is given that this is a random sample which I have drawn from the normal population. So we know that expectation of x1 is equal to mu. It is given because it has been taken from the normal population. And it is also given that variance of x1, or rather variance of xi and expectation of xi is equal to 1, because it is true for all values of I. So I write it for all I, right? For all I from 1 to n. Or rather, this notation may be slightly confusing, so I remove this and I write the general term. So for I is equal to 1, 2 up to n. So expectation of x1 is mu, x2 is mu, x3 is mu, and all terms is mu. Now there is a definition which we have studied in detail earlier. So if I ask you what is variance of xi, so you will say that it is expectation of xi square minus expectation of xi whole square. So this implies what? Variance of xi is given, that is 1, and expectation of xi square is something that I have to calculate, and minus expectation of xi is what? Expectation of xi is mu, so this is minus mu square. So what do I get? I get expectation of xi square is equal to 1 plus mu square, and this is for all values of I 1, 2, 3 up to n. So if I continue with this expression, so using this information that I have got, I am now moving ahead with expectation of t. So what is expectation of t now? It is 1 by n, and expectation of x1 square is equal to 1 plus mu square, right? Expectation of x2 square is also equal to 1 plus mu square, and so on up to expectation of xn square, that is equal to 1 plus mu square. So this is equal to what? This is equal to 1 by n into n times 1 plus mu square. So this n and n cancel. What I get is 1 plus mu square. So we have proved that expectation of t is equal to 1 plus mu square, and this was my aim. So now I can conclude that t, that is given by 1 by n summation of xi square. Let me write here in the this in the next page, otherwise some of you may be confused. So I am moving ahead in the next page. Okay. So what we have concluded? We have concluded that t, which is given by 1 by n summation of xi square, I varies from 1 to n, is an unbiased estimator of mu square plus 1, and this proves the result. So this proves the result. This is a very important problem that I have discussed. I hope you have understood. In case if you have not, please rewatch it and let me know your doubt in the comment section. I am moving ahead with the next problem. This is also a very important problem. This is very important. So if t is an unbiased estimator for theta, it means what? That they have already given this information, that expectation of t is equal to theta. Let me call it 1. We have to show that t square is a biased, it is biased estimator for theta square. Means what we need to show? So we need to show that expectation of t square is not equal to theta square. So how to show that? To show that, I am going to use the definition of variance of t. What is variance of t? Variance of t is expectation of t square minus expectation of t whole square. And this gives me what? This gives me expectation of t square is equal to variance of t, or let me write this term first rather. So I take this term in the left hand side, so I get expectation of t whole square plus variance of t. So this gives me what? This gives me expectation of t square is equal to, as expectation of t is equal to theta, this is equal to theta square plus variance of t. Now if you have a random sample, then variance of t is always positive. You know, variance is always positive. So since variance of t is greater than 0 for a random sample, and here we note that expectation of t square is equal to theta square plus something positive. So it certainly means that expectation of t square cannot be equal to theta square. So it means what? That it means that t square is a biased estimator of theta square. So as simple as that. It is a very simple problem. We did it very quickly. Now let us talk about this problem, and this problem is also important. All the problems that I am doing are important problem, and unbiasedness is the very first topic, so it is very likely that they may ask you this kind of question. So the next thing we have to show that this is the estimator is an unbiased estimate of theta square for the sample x1, x2, xn drawn on x, which takes the value 1 or 0 with the respective probabilities theta and 1 minus theta. Now this is important. I don't know how many of you remember, but I have talked about this kind of distribution in Bernoulli population, right? So if we are taking any value either it is taking the value 1 or 0, and its probability is theta or 1 minus theta. So it means what? That this is being taken from a Bernoulli population. So there is a very important characteristic which I am going to write, and then I will talk. The characteristic is, I am writing it, since x1, x2 and xn, this sample is a random sample, from Bernoulli population. Right, with parameter theta, I hope you remember this thing, that probability of success is theta, probability of failure is 1 minus theta. So the parameter that we associate with Bernoulli population is theta. Right, we define a term that is t. What is t? T is the summation of xi, where I varies from 1 to n. So this is the characteristic I was talking about, that if I am taking a random sample from a Bernoulli population, then this parameter t or this term t follows a binomial distribution with parameter n and theta. Right, because I am taking the values from x1 to xn, there are n sample values. So if I take the summation of xi, I varying from 1 to n, this will follow a binomial distribution with parameter n and theta. Okay, so if t follows the binomial distribution, you can remember this. I highlight this, that this is a result which you can remember, that if you draw a random sample from a Bernoulli population, then this t which I am defining like summation xi I varies from 1 to n follows a binomial distribution. Okay, now since t follows the binomial distribution, it means what? That expectation of t will be equal to n theta. You know that mean of the binomial distribution we have studied earlier is n into p, and variance is n into p into q. So here in place of p we are using the parameter theta, so expectation of t is equal to n theta, and variance of t is equal to n into theta into 1 minus theta. Right, now we have to show that this is an unbiased estimator of theta square. It means that we are taking the expectation of this. Expectation of what? Summation of xi into summation of xi minus 1 divided by n into n minus 1. So in our terminology, this summation of xi I am representing by t, so I can write expectation of t into t minus 1 divided by n into n minus 1. So here I can write 1 by n into n minus 1, and using the properties of expectation, I can write it expectation of t square minus expectation of t. I hope you got it. It is t square minus t, so expectation of t square minus t is expectation of t square minus expectation of t. Continuing here, when you write the answer, you should write vertically, but since I want to save a space, I am squeezing the things in between. So I am writing n into n minus 1. And what is expectation of t square? So that I don't know. I know expectation of t, but I don't know expectation of t square. So before I calculate this term further, what we are going to do, I am going to remove this part, and let us first calculate that expectation of t square. So to calculate expectation of t square, I am going to write what is this characteristic, that variance of t is equal to expectation of t square minus expectation of t whole square. Whenever we have to calculate this expectation of t square, we are using this formula. In the previous problem also you have noted that to calculate expectation of t square, I was using this formula, that is variance of t. Now this gives us what? Variance of t is given to be, this expression is given to be n theta into 1 minus theta. Right, so I can write it expectation of t square is equal to expectation of t whole square and plus variance of t. So it means what? It means that expectation of t square. What is expectation of t whole square? That is n theta. N theta whole square, that is n square theta square. And what is variance of t? That is n theta into 1 minus theta, this term. So if you allow me, I can write n theta minus n theta square. Okay. And I hope it is making sense to you. So here this is the value of our expectation of t square. Since we don't have a space, I am moving into the next page. So that continuing that previous term, so I was calculating expectation of t into t minus 1 by n into n minus 1. And here it was, you can see it, it was 1 by n into n minus 1. So I write 1 by n into n minus 1. And here I have to write expectation of t square. So expectation of t square, I have got n square theta square. So I write n square theta square, and plus we have n theta minus n theta square. So n theta minus n theta square, and then from this I have to subtract minus expectation of t, so that is minus n theta, right? I hope you got this point. Let me repeat. I have this expression, right? So let me call it 1, and let me write here from 1, right? So from 1 I am substituting the value of, in this expression, expectation of t square that I have calculated here, and then minus expectation of t, which is n theta. So this is what we are getting. Now you can see this n theta and minus n theta term is cancelled. So I am getting 1 by n into n minus 1, and from this you can take what common? You can take n theta square common. So from this you will get n, and from this you will get minus 1. So did you realize what you got? N and this n cancel, this n minus 1 and this n minus 1 cancel. So what you got is equal to theta square. So it means what? That expectation of this is equal to theta square. And what was t? T was basically summation of xi. So summation of xi into summation of xi minus 1 divided by n into n minus 1 is an unbiased estimator of theta square. So this is what we wanted to prove, and we have proved it. Okay. So moving ahead, let us quickly do this third problem. Right? Not third, this is the fourth problem. And as you know that problem solving is important aspect of understanding any concept. So that is why we are solving many problems. So how to solve this problem? The problem is that let x be distributed in the form of Poisson distribution with parameter theta. You remember I earlier talked about that what is the parameter of Poisson distribution. So we used to call it lambda, that is the mean of the distribution. But here we are calling it theta, no problem, I will call it theta. Show that only unbiased estimator of exponential minus k plus 1 theta. So this is basically minus e to the power minus k plus 1 into theta. And it is given that k is greater than 0, means k is positive. So we have to show that for this this term, the estimator given by this formula is an unbiased estimator of exponential minus k plus 1 theta, so that tx is greater than 0 if x is even, and tx is less than 0 if x is odd. So which is very clear, since k is positive, so minus k to the power n, anything even will be greater than 0. So tx will be greater than 0 if I take x even, and tx will be less than 0 if I take x odd. So this is obvious. So basically what we have to prove? We have to prove that tx, which is given by minus k to the power x, is an unbiased estimator of e to the power minus k plus 1 into theta. This is just another way of writing it. So I think by now you are mature enough. So what is the process? We will calculate expectation of tx, and I have to show that this value will be equal to this value. Now how do you calculate expectation of tx? So it is basically expectation of minus k to the power x. And since this x follows the Poisson distribution, to calculate the expectation, you have to write summation. You remember the formula of calculating the expectation? Expectation of x is equal to summation x into px. Do you remember this? And for a Poisson distribution, if I ask you what is the probability for x is equal to x, so you remember it is e to the power minus lambda, lambda to the power x by factorial x. All these things that I am writing with red ink actually is not the part of the solution. This is just to explain you. So I am writing expectation of minus k to the power x. So I have to calculate minus k to the power x, because this capital X can take values small x, and this small x varies between 0 to infinity. Because in case of Poisson distribution, the random variable x can take value from 0 to infinity. And then probability of x is equal to x, that is e to the power minus lambda, but I am calling it theta here. So e to the power minus theta, theta to the power x by factorial x. I hope you have understood this term. Now we have e to the power minus theta, which is not dependent on x, so it is a constant. I can take it out of summation, and here I get x varies from 0 to infinity, and this is minus k to the power x, and this is theta to the power x. So I both can combine. I can write minus k theta to the power x by factorial x. So this is equal to e to the power minus theta. If I take x is equal to 0, I get 1. If I take x is equal to 1, I get minus k theta by factorial 1. If I take x is equal to 2, so I get plus k theta square by factorial 2. And minus, if I take x is equal to 3, I get minus k theta cube by factorial 3. And this is plus so on. So basically what we are getting e to the power minus theta into e to the power minus k theta. I hope you remember the exponential function. Again, I am using the red ink, means this I hope you know. So this is e to the power minus x is 1 minus x by factorial 1 plus x square by factorial 2 minus x cube by factorial 3, and so on. So here we have the same expression. So continuing this, I will write it is e to the power minus common k plus 1 into theta. Right. So expectation of tx is equal to e to the power minus k plus 1 into theta. So tx is an unbiased estimator of e to the power minus k plus 1 theta. So this was the problem number 4. We are 32 minutes in the video, so let us quickly solve. This is a very important problem, may be asked in exam, and you will also be noticing later that in testing of hypothesis I will be using this result. So be very careful. This is a very interesting problem, so I want all of you to be focused. So what we have to do, we have to show that the sample variance of a sample drawn from normal population given by this expression is an unbiased estimator of the population variance, which is sigma square, right? What I want you to note here first is that in your previous classes you might have studied that to calculate the variance we use the formula 1 by n summation xi minus x bar square. But it can be shown that this formula, if I use this formula to estimate the population variance, that will not be a unbiased estimator. So what is the unbiased estimator? So we make a small change in the formula, and in place of n we are writing 1 by n minus 1. So here this n is being replaced by n minus 1. And what we have to do, we have to prove that this is an unbiased estimator of the population variance, that is sigma square. So how to do that? We already have done many problems, so now we are confident. We are going to calculate the expectation of s square. And somehow after manipulation I have to show that it is equal to sigma square. So I am going to calculate expectation of 1 by n minus 1 into summation I varies from 1 to n xi minus x bar whole square. So this is equal to expectation, I can write 1 by n minus 1 is constant, so I can take this 1 by n minus 1 outside. So I write 1 by n minus 1, and expectation of this summation, and I'm not writing I varies from 1 to 1 to n. I think it is clear. So I'm just writing summation and I'm expanding it. So I will get xi square minus 2 into xi into x bar and plus x bar whole square. Okay. Now this is equal to expectation 1 by n minus 1. I don't know why I'm missing this term again and again. So I write 1 by n minus 1 and expectation of summation, and just look at this thing carefully, xi square. And one thing that I want you to note, that this summation is going to run over these three terms. Okay, so I am first taking the summation over the first term, and let me rewrite it. So I am writing it summation of xi square, right? Summation, oh, what is happening? Summation summation xi square minus, now if I look at this term, I can take 2x bar out and I will get summation xi and plus summation x bar square. So I am writing it n into x bar square. I don't know whether you understood this or not, because see, here the summation runs from I varying to 1 to n, and here also I varying from 1 to n, I varying from 1 to n. So if I look at this expression, for how many terms are of this type are there in this expression? There are total n terms. There are total n such brackets, and in for I is equal to 1, I will get x1 square minus 2 into x1 into x bar plus x bar square. Then for I is equal to 2, I will get x2 square minus 2 into x2 into x bar plus x bar square. So this x bar square will come how many times? It will come n times for I is equal to 1, for I is equal to 2, for I is equal to n. So if I am taking the summation, this will be n into x bar square. Okay. One more thing I want you to note, that if I ask you what is x bar, you will say that it is summation of xi divided by n. So it means what is summation of xi? This is n into x bar. So for the summation of xi, let me write the next step. I am writing 1 by n minus 1 into expectation summation xi square. I am not writing this I varying from 1 to n, and here it is 2x bar, and this thing is nothing but n into x bar for this summation, for this one, right? So for this I am writing n into x bar and plus n into x bar whole square. So what is the next step? I get 1 by n minus 1 expectation of summation xi square minus, and it is 2 into n into x bar square, so minus 2 nx bar square and plus nx bar square. So I will get n into x bar square, right? Now since we don't have a space, so I have to move to the next page. So I am moving to the next page. So here we have, what term we have? So this is the term we have. You can see 1 by n minus 1 expectation of summation xi square minus nx bar square. Now I'm going to take the summation term inside. Sorry, this expectation. So this can be written as 1 by n minus 1, and expectation of summation of xi square can be written as summation of expectation of xi square. I hope you understand. Xi square means x1 square plus x2 square plus xn square. Then expectation of x1 square plus expectation of x2 square plus up to expectation of xn square. So that I am writing, and minus n into expectation of x bar square. This is what we are getting. So we have to calculate two terms. One is what is expectation of xi square, and another is what is an expectation of x bar square. So this is basically what? This is basically expectation of s square. I am writing here. This is basically expectation of s square. Let me call this 1. And I am now going to focus on expectation of xi square. So you remember what is the variance of xi? Variance of xi is equal to expectation of xi square minus expectation of xi whole square. So this will give me what? This will give me variance of xi is sigma square, expectation of xi square I want to calculate, and minus expectation of xi is equal to mu square. So from this I am getting expectation of xi square is equal to sigma square plus mu square. It is given in the problem that I have taken the sample from a normal population. So in case of normal population, x follows the normal distribution with parameter mean, that is mu and sigma square. Means expectation of this any variable is mu and variance is sigma square. Now what is expectation of x bar square? This you need to understand carefully. So first of all, to calculate expectation of x bar square, we need to know what is expectation of x bar. So what is expectation of x bar? Expectation of x bar is 1 by expectation of 1 by n. And what is x bar? X bar is 1 by n into x1 plus x2 up to xn. This is how you write x bar, sorry. So using the property, it is 1 by n into expectation of x1 plus expectation of x2 dot 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 up to expectation of xn. So we get what? We get expectation of x bar is equal to 1 by n, and expectation of x1 is mu, expectation of x2 is mu up to mu. Right, so it is equal to 1 by n into n mu, so that is equal to mu. So expectation of x bar is equal to mu. What is variance of x bar? So variance of x bar will be equal to variance of 1 by n, and x bar is given by x1 plus x2 up to xn. So this can be written as, let me write it here in the bottom. So this will be equal to, let me continue here. So this will be equal to 1 by n square. I hope you remember the property of variance. And then variance of x1 plus variance of x2 and up to variance of xn. This is a very important result I am proving here. So this is 1 by n square. Variance of x1 is sigma square. Variance of x2 is also sigma square. Variance of xn is also sigma square. So what I get? I get 1 by n square into n sigma square. So that what I get? I get sigma square by n. So this result that I have proved, I will be using it in the coming videos also, that if x follows the normal distribution with mean mu and variance sigma square, then x bar follows the normal distribution with mean mu. That you can see that we are getting mean mu, that is expectation of x bar is equal to mu, but variance is sigma square by n. So if x is a random variable, if x is a random variable which follows the normal distribution with parameter mu and sigma square, then x bar is also a normal variable which also follows the normal distribution with parameter mu but variance sigma square by n. Right, so you need to keep this result. This is a standard result and may be asked in multiple choice question as well. So now I have to move to the next page. So this is our equation 1 which I have left here. So expectation of s square is this, and I wanted to calculate expectation of xi square. So here I have calculated, that is expectation of xi square, that is sigma square plus mu square, and this is true for all I from 1 to n, right? And I also have calculated what I have calculated, that is variance of x bar is equal to sigma square by n, and expectation of x bar is equal to mu. So there is one thing that I want to calculate. We already have calculated this value. I want to calculate expectation of x bar square. So using this result again, what is variance of x bar? Variance of x bar is expectation of x bar square minus expectation of x bar whole square. So variance of x bar is sigma square by n, that I just calculated, and I want to calculate expectation of x bar square. So that is expectation of x bar square, and minus expectation of x bar that I have just proved is equal to mu. So here I write minus mu square, right? So it means what? That expectation of x bar square is equal to mu square plus sigma square by n. So now I am going to put all these values in the equation number 1. So expectation of s square is equal to 1 by n minus 1 into summation xi square, and this I varies from 1 to n. So actually for each value of I from 1 to n, if I write I values varies from 1 to n, I am getting sigma square plus mu square, right? You see it, that is what I have completed here, that expectation of xi square is equal to sigma square plus mu square, and that is for each value of I, that is I1, I2, In. So if I add it n times, I will get sigma square plus mu square into n, and minus n times. What is expectation of x bar square? That is mu square plus sigma square by n. So this result that I have actually proved here, it could have been used directly also, like this part here from this onwards I could have directly written, but just for your clarity I have proved. Now we are in the very last step. So you can see n mu square, here mu square into n will be cancelled, and here n into mu square will be cancelled. So what I will get? I will get 1 by n minus 1, and from this I will get sigma square into n, and from here this n and n cancel, so I will get sigma square, right? So I will get 1 by n minus 1 into n minus 1 sigma square. So this n minus 1 and n minus 1 is cancelled, so I get expectation of s square is equal to sigma square. So this implies that is s square, which I started with 1 by n minus 1 summation xi minus x bar whole square, is an unbiased estimator of sigma square. So please try to write all these answers on your own. This is a very important question, and it has taken some time to prove it, but it is interesting. And you also will note that when I'll be talking about testing of hypothesis, to calculate the variance, I will be using this result only, that is 1 by n minus 1 xi minus x bar square. Just quickly see what we have done. We started with expectation of s square, and up to this I have just done the manipulation, right? So I got expectation of summation xi square minus nx bar square, and I wanted to get summation of xi square, and I wanted to get here summation of xi square and expectation of x bar whole square. So to get summation of xi square, we have used this property, that is variance of xi is this. So from this I will get expectation of xi square, right? And to get expectation of x bar square, I have first calculated what is expectation of x bar, so that I got is equal to mu. Then I calculated variance of x bar, and that I got sigma square by n, and I told that x bar also follows the normal distribution with mean mu and variance sigma square by n. And then what I did, then I calculated this term, that is variance of x bar is equal to expectation of x bar whole square minus expectation of x bar expectation of x bar square minus expectation of x bar whole square, and this I calculated as sigma square by n. This I wanted to calculate, and this I calculated mu square. So expectation of x bar square is equal to this. Now I have got all these values, I substituted in equation 1, and I proved that this is equal to sigma square. Okay, so this is the end of the video. I discussed 5 problems. I introduced the idea of estimation. And some student request me to create a smaller videos, but if you want a smaller video, I will be able to solve just one problem. If you want many problems, I have to create longer formats of the video. So in case if you enjoyed the video, like it, share it, and just to motivate me, you must have to subscribe my channel. So that is all from my side. Thanks for watching. In the next video, I'll be talking about consistency and efficiency. Have a great day.